Thank you. Good morning, everybody. I'll begin by reviewing quickly the main highlights of yesterday's talk, the main points. So, and if there were many questions between then and now. If some additional questions arise, let me know. So we began with the general idea that if you have a discrete system on the lattice, they call it a quantum antiferromagnet, this type of Lagrangians. This type of Hamiltonians are called quantum antiferromagnets because J is typically positive. And so people know that those kind of Hamiltonians can be driven to special loci by tuning these parameters J and other parameters so that the correlation length on the lattice blows up. Then you typically get a conformal filter with a Lorentz invariance, which is emergent, and a light cone in the continuum. And so that's how conformal filter arises in many examples in physics. There are, of course, ways in which conformal filter arises from string theory and high energy physics, but this is a way in which it arises from discrete systems.
Can I ask the question at any stage?
Yes, at any stage.
I just want to, can you clarify why it's necessary that Lorentz invariance emerges?
Well, I'm just talking about those cases where it does, because the theory of line defects is mostly not developed for
systems in the lab.
Yeah, I mean, you can. There is very little known from the theoretical point of view on line defects in Lipschitz or Schrödinger systems. So, but in CFTs, there is much more that we know.
Since you mentioned that, can you remind me what are Lipschitz and Schrödinger systems?
Well, those are various continuum filters which don't have a light cone. Okay? Okay?
Well, whatever you wish.
Yeah, non-relativistically invariant continuum quantum filters. So,
Certain type of
yeah, gapless non-relativistic quantum filter. They're called Lipschitz or Schrödinger, but I mean, the theory of line defects is not very well developed, and there aren't that many strong results in that field. So I'm just focusing on CFTs also because it's a high energy physics audience. So the line operators are more natural, are natural from that point of view as well. Any other question? Okay, and then the next idea is that you can pluck out some lattice site, replace it with some impurity, some kind of generic piece of garbage, which is described by an impurity Hamiltonian, and the impurity Hamiltonian only acts on lattice sites which are nearby the question mark. So it's localized in space. And then when you're near this phase transition point in the bulk, this turns into a line operator in the continuum conformal filter. And the line operator is conveniently taken to be in the time direction. In that way, it changes the Hilbert space, because the impurity could have its own Hilbert space, and it describes the new vacuum. You have to find basically the new vacuum. So the name of the game is that you have to find the new vacuum in the presence of this time-like line defect. All right? Then there is the idea that once you have this relativistic setup with the line operator, you can also do a Wick rotation. And so that's why line defects are used interchangeably with line operators, because you can do the Wick rotation and think about it either way. The next idea we covered was that a line operator in a conformal filter is not necessarily conformal from the get-go. The impurity Hamiltonian may have its own coupling constants, which need to be tuned for the line operator to become conformal. And if the line operator is conformal, so those couplings are tuned to the conformal fixed point, then this whole system, namely the bulk plus the line operator and the new vacuum, would be invariant under SO2R times SOD minus 1. And in addition, okay, so this is the statement of a conformal line defect. Then we discussed that there is a bulk defect OP. So bulk operators can be expanded in defect operators. I was asked several times between back then and now, whether it makes sense to actually put bulk operators on the defect, and the answer is no. You see, there is a singularity in general, so you have to expand them in this fashion. And in particular, the contribution of the unit operator here is interesting experimentally, because that allows you to determine the one-point functions by this one coefficient AI with no index, since it corresponds to the unit operator. And you have some consistency conditions of the bootstrap type, that you can compute two-point functions in the bulk in two ways, and there is some consistency, that there should be some consistency between those two approaches. Okay, so then we discussed that conformal, yes?
You talked about the lack of positivity here.
Yeah.
Can you elaborate on that a little bit? Why do we have positivity in the...
It's just that these coefficients, the coefficients AI, in particular the one-point functions, they don't have to be positive. So even the expectation value of a bulk operator like phi squared could be negative due to the line defect. There is no. So you know that in the conformal bootstrap, the positivity of various coefficients was important to get rigorous constraints. So here you can get non-rigorous constraints. It's hard to get rigorous constraints.
What is non-rigorous constraint?
Well, it just means truncating, like assuming that only the first 10 defect operators are important, and then it becomes a linear system in 10 variables, and you can try to find you can try to find solutions and hope that they converge to some physical solution.
You can't find a region.
You cannot find a region. You can just find some solutions to a finite truncation of the system.
And what is the reason that we don't have positivity, whereas we did?
Well, it was a different problem. Here we have Green's functions in the presence of this impurity, and there the problem was the 4-point function of identical operators. So here there is some sort of manifest reflection symmetry that makes everything positive. And when you study this problem, there is no manifest reflection symmetry, because if you reflect around, there is an arrow on the line. The line goes up, so there is no reflection symmetry, and there is nothing positive. You cannot cut.
And this is why you said that if we have two lines, then perhaps...
Yeah, so yeah, people are considering, there is now some people trying to put another line operator, and then something becomes positive maybe.
Are there any bootstrap results?
Yeah, I'll mention some when we get into more advanced questions. Okay. Then there was the idea that every line operator that is every conformal line operator has a universal operator, which is called the displacement operator, and it carries an index which is transverse to the line. And its physical meaning is that if you insert it on the defect, so this is a defect operator, therefore it can be inserted on the defect. So if it is inserted on the defect with a general coefficient that's varying in time, the physical meaning of that would be to change the shape of the line accordingly by the coefficients with which this operator is inserted. And this operator appears universally in the non-conservation equation of momentum. So this operator just measures the violation of momentum conservation due to the line defect. It's universal. We call it a displacement operator. Sometimes in condensed matter it's called the tilt operator, but usually displacement. Okay?
Tilt?
Tilt. Yeah, tilt. Because you can use it to tilt. We usually, but yeah, I'll just call it displacement operator.
So we modify the Hamiltonian correspondingly?
Yes. The physical meaning of this is that the Hamiltonian has been modified in such a way that at some moment in time the impurity has begun moving, and then it ceased moving. So it generates some response. It could generate radiation, it could change the vacuum. So the state after this could be very different from the state before, and you can compute stuff. Okay? So the next thing is that I mentioned that if all the one-point functions vanish, all those numbers vanish, it means that the displacement operator vanishes as an operator. This idea is physically kind of obvious, because if the system has no response to moving the defect, then one-point functions wouldn't see the defect either. And I will just call in these lectures this situation, I'll say that the defect is screened, that the impurity is screened. It's not entirely precise, because there are topological line operators in QFT and people don't like to think about them as trivial or screens. They are like the most important. They are interesting. The topological line operators are the main characters of TFT. So, but anyway, for these lectures, this would be considered to be a trivial defect because you cannot see it in correlation functions. And if the defect is indeed screened and trivial, the bulk defect OPE takes this form. It's just a Taylor expansion around an imaginary line where nothing exists, in fact. Just an empty place. Okay, so this is what I said yesterday.
You mean by the triviality of the defect that it can be moved
Yeah,
without
without punishment.
then D hat is still non-zero.
No,
You have
it's,
to move it.
it's zero as an operator.
Commute in a Hamiltonian or something that is zero.
No, it is zero as an operator. Do you see what I mean? It just means that the partition function with this shape is the same as the partition function with the previous shape. So that means that as an operator, this has to vanish. Yeah.
Did you say before that when you put an impurity, an expectation value of an operator which looks okay, like phi squared, it can become negative?
Oh, sure, yes.
So is it an issue of regularization? Does it depend on the...
No, it's completely scheme. These coefficients AI are completely scheme independent.
So how, so can
Or
you
were they?
explain how phi
This
squared becomes negative?
Why not?
Looks like a positive operator.
Right, but when you compute phi, you know, the expectation value of phi squared in the normal vacuum with no line defect is 0. So this is the definition of normal ordering.
Okay, so you remove stuff.
Well, I'm saying without a line defect,
Yeah.
all the one-point functions vanish. So it just becomes, yeah, you could say that it's huge, like some UV, but due to the defect, it became a little bit smaller. So, any other questions? Okay, very good. So this finishes the review. Today, I want to begin with 3 topics. One is the homework question to determine the one-point function of the energy momentum tensor, the energy density that's created by an impurity. So I want to show you the answer to that question. Then we'll discuss the energy that is locked. So there is a question. So this was a discussion of how momentum is violated by the defect. I want to tell you one surprising fact about energy conservation in the presence of a conformal defect. And then we'll begin to discuss our G flows on defect and entanglement entropy and these kind of things. So first, the one-point function of T mu nu. So due to the symmetries of the problem, you have to decompose the one-point function of the energy momentum tensor in these 3 tensors. The first T00 just means that you measure the energy density due to the defect. This one measures the momentum density, but we don't really think, I mean, physically it's clear that there is not going to be momentum density outside of the defect because we're supposed to have reached the vacuum. And in the vacuum, having non-zero momentum flow means that you're not yet in equilibrium. So the answer is that this vanishes. This is given by d minus 2 over d times some new coefficient h times 1 over r to the power d. This is given by h r over d, xi, xj, x squared, minus delta I j over a d that seems wrong. I just fix it. 2 over d delta I j. Okay.
You argue that T0 I 0 because of the symmetry of some D.
Well, that's not quite sufficient. You could have written something like this. this would be consistent with the symmetries. But it would not be consistent with conservation, because if T0i is non-zero, it means that this must be time dependent because of the conservation equation, which would then mean that you're not yet in equilibrium, because you have a time dependent one-point function. And that violates SL2R symmetry, which says that it should be time independent. So a conformal defect cannot have momentum density, it can have energy density, and it can have something interesting here is that in D equals 2 everything vanishes. This will be super crucial when we discuss entanglement entropy. So for D equals 2, for defects in 1 plus 1 dimensions, everything vanishes. You see that this vanishes, and this vanishes kinematically, because when the number of dimensions is 2, this cancels out, and there is only one transverse coordinate. So this is 1 minus 1.
What's the intuitive reason for this?
Intuitive reason for this? I don't know. So an impurity in 1 plus 1 doesn't generate energy density. You see it in these formulas, and it will be crucial, very crucial soon.
The second one comes from tracelessness.
Right, so to answer this problem, you have to use tracelessness, conservation, and the symmetries. And so everything is fixed by one coefficient, which is called h. You see? There is one unknown coefficient that is model dependent, but either way, in D equals 2, the whole thing vanishes.
Maybe D equals 2 should be K somehow, but you cannot do it on one dimension. So
No, but the dimensional analysis does not preclude energy density, because you could have just put D equals 2. It would decay 1 over distance squared. What's the problem? It's just an interesting miracle that that this vanishes and this vanishes. Okay? But it will be very crucial soon. Yeah.
What's the, sorry for a stupid question. What's the difference between R and X, like X squared, R?
Oh, I'm sorry, yes. It's the same. It's the transverse defect, transverse distance.
Yeah.
Yeah. Okay. So this is the answer to the question. Now I want to discuss.
H
Not
is
just the
determined
space.
or-
D is not
H is model dependent.
No, no. D is not just the space dimension.
D is space-time dimension.
Space time. So it's one.
Yeah, I'm always in D minus 1, 1 signature. So this is the number of space-time dimensions.
If you don't know what H is, could be 1 over D minus 2.
Well, H is a number, you fix D. H is just, I'm just saying you cannot write a consistent, whatever it is, in D equals 2. For a conformal defect, you just cannot write the right-hand side that's not vanishing. Just because there is no tensor to write here. And so this has to vanish. Now a conjecture, a conjecture that would be, so what do we know about this H? It's of course model dependent. But we know that H is non-negative, which is intuitively very good, because it means that the energy density created by the defect is non-negative. Okay, so we know this rigorously. We can prove this by some methods. A very interesting question that I do not believe is settled is to prove that H equals to 0 if and only if all the AI's are 0, if and only if the displacement operator vanishes. So I believe that H equals to 0 is equivalent to the triviality of the defect. But I don't know if it's true. This is a conjecture.
These expectation values are normal order.
So actually one of the AI's is H, right? One of the AI's is the one-point function of the energy momentum tensor. So I'm just saying it's sufficient that H vanishes for everything to be trivial, I suppose. Yeah.
So you take normal order operators?
Yeah, this is in a convention where T obeys the conformal word identities and its one-point function vanishes in the normal vacuum.
So in the sense it's normal order.
It's whatever it needs to be so that it measures the response to the metric in the normal vacuum. You can call it normal ordering. Yes.
Maybe it's the same question, but why specifically like the number of special dimensions plus 1? Like for example, if I really want to charge I would expect it to go like.
No, but let's do the charge. The charge is an excellent example. Let's take a charge Q.
Yeah.
What did we learn in school? What's the electric field?
Yeah, one of our out to the
Second
minus
power.
2 in your-
Let's do 4 dimensions.
Oh, okay. So
1 over r squared.
Yeah.
So what is the energy density? It's the electric field squared.
Oh, all right. Yeah.
So
Okay.
actually, this is going to be one of the simplest examples of a line defect. It's a point charge. And it obeys this axiom, and h is 1 in some convention. Yeah. So for a point charge in 2 plus 1 dimensions, it's not going to work. You're not going to get 1 over r cubed. And the reason is that 2 plus 1 dimensional Maxwell theory is not a conformal field theory. The electric charge has dimensions. The electric coupling constant has dimensions, so it's not a conformal field theory, and this doesn't work. But if you look at the conformal U1, there are conformal versions of U1 plus matter, blah, blah, then it would work. It would be 1 over r cubed. Any other? Okay. So this is the first topic I wanted to cover.
So you're saying that H is positive is an assumption? Or
No, this is proven. This is proven, and this is a conjecture.
Is it proven
Based on
assuming positivity of the energy density?
Well, that would not be a proof. That would be a circular argument. If you just assume that this 0, 0 has to be positive. I think it's a little bit more than that. I think you can use some sort of average null energy condition to prove it. I think so.
Sometimes you need some
Yeah,
assumption
yeah.
of positivity of something.
Yeah. Yeah, I mean, we know that in quantum field theory, the energy density could be negative in some region of space. But if H was negative, it would be negative everywhere. So it's just too dramatic to allow. And you can actually rule it out.
So unitarity, for example, is not an input here.
No, of course it is.
It is.
Yeah, if you use the energy conditions, it's average energy conditions, so you use unitarity. Yeah. Okay? So this is topic number 1. The next thing I want to explain is a little bit difficult to understand. It took me a lot of time to understand that. So we discussed the violation of momentum conservation, and now I'm going to talk about energy conservation. So we have a Hamiltonian, which is the sum of the bulk and impurity Hamiltonian. And we have some, we have this line defect. So what is the statement about conservation of energy? What should be the right statement about energy conservation? Of course, the energy momentum tensor is conserved away from the defect. But what is the correct equation for a t0, 0? We take a time derivative at some x and t, plus we take the divergence of 0I at some x and t. And of course, this vanishes for as long as you're away from the defect, because that just measures local energy conservation away from the defect. But suppose you're really motivated to try to take the x equals 0 limit in the same way that we took the x equals 0 limit here, and we define the displacement operator. So you could ask, what are the contact terms due to the defect? And the answer seems to be obvious. Some energy can be stored in the defect for some time. It could evolve. Then the energy would come out. So there will be energy conservation. But energy can be exchanged with the defect. So that means that there is a new operator here, which comes with a delta function, which is called theta of t. And it measures the energy density on the defect.
In what form does it being absorbed by the defect? I mean, it's not a kinetic
Well, you could,
energy, it's not
no,
potential.
think about the Hamiltonian interpretation, where h is the h of the bulk plus h impurity. So there could be some quantum states on the spin that we added, the Kondo spin. The energy, there could be some, you could go to some excited state in that quantum spin. So just think about inserting a quantum spin with s degrees of freedom at some point here, let's say. So you could imagine some excitation coming in, exciting this atom or this nucleus to a higher state. You would be in this higher state for a while, and then it would decay. So the atom of this impurity could be excited. So this operator theta would be a dimension 1 operator on the defect, measuring the energy density of the defect, the intrinsic energy density operator. This is unlike the displacement operator, whose dimension is 2. Where is the difference? The difference is that here there was a derivative, but here there is no derivative. There is a time derivative here. What did I do? I did some. I just did something. Yeah, sorry. So this would have been delta equals 2. It would have been a delta theta would have been a delta equals 2 operator on the defect. With secretly it has 0, 0 indices, but we don't write them because on the defect it would look like a scalar. Okay. So in addition to the displacement, you might have expected a scalar operator that measures energy that measures the energy localized to the defect. Let me just make sure that everything here is correct. So this
Why is that equation different?
no, it's the same.
So that's the same as D?
I think on the left side, I was obviously shown.
There's something that I messed up. Well, this equation is not the same as this one because this is the momentum conservation. This has an I, and this is the zeros component of the energy momentum tensor. Okay, so you could ask, what do we know about this operator theta of t? What do we know about this theta of t, which is basically how much energy is stored on the defect? And the deep claim is that at the fixed point of any line operator in any number of dimensions, this vanishes. This is more difficult to prove. And it's kind of a deep statement. It says that conformal defects cannot store energy. But when you're away from a fixed point of the renormalization group of a line operator, then you can store some energy. You could excite this atom, it could decay. But when you're at a fixed point, then it cannot store energy anymore. This has a more lengthy proof using unitarity that I cannot reproduce here. But I just wanted to, I'll give you a qualitative argument now. So no energy stored. So that means that when the defect is conformal, if you try to store energy, it would always spread into the bulk. So there is no energy stored on the defect. Okay. This is important to know.
You that it can be excited the state of the spin. So you said that if
Yeah,
it's
I said
conformal, it cannot.
Right, and if you tune it to the fixed point, then it cannot happen. Right, there cannot be stored energy at the defect at the fixed point. If you're away from the fixed point, of course it can store energy. By the way, the same thing is true for boundary CFT. If you are more familiar with boundary CFT, a conformal boundary CFT cannot store energy.
The way we define it is defined up to a constant. So
Right.
That's the constant.
Right. It's an excellent question. So I'll get to it. It could be that theta is a constant. So that means that there is like constant energy density of the defect. This will be very important soon. I actually wanted to mention it, but I forgot. This is some counter term that's called the cosmological constant term on the line defect, and we'll discuss it when we discuss partition functions. But the main point is that energy cannot be exchanged with the line defect. Maybe there is some constant that's scheme dependent, but you cannot exchange energy with the line defect.
No.
Yeah.
Isn't it maybe a request time translation? Or change your energy and time?
No, I mean, in a system that preserves energy, in principle, there could be energy stored on an
But
on a
it would be a
defect.
constant, which will not vary with time.
Yeah, a constant that doesn't vary in time. Yeah, a constant that doesn't vary in time is fine.
So it's theta dot equals 0? So it's theta dot equals 0? Like the time derivative of theta vanishes in the box equation?
Yes.
Okay.
I mean,
Yeah.
you want me to put a dot, I'll put a dot, but this constant is scheme dependent. So you can choose a scheme where it actually is 0. So I don't want to put the dot, it looks too mysterious. Just put it like this, that there is just no energy stored in the, other than some scheme dependent constant, there is no energy stored at the defect. Yeah?
If you use the scheme in which theta equals 0
the IR?
I don't want to discuss RG flows yet. I'm talking about conformal defects. This is a deep property of conformal defects that they cannot store energy. Yeah.
This is just for defects that are time independent?
Yeah. Time-dependent defects. That SO2R symmetry includes this assumption implicitly because there's time translation symmetry. You'll see soon why this is also kind of important. I'm just reviewing it. Okay. You just see that I don't want to say anything. Yeah. Okay, so these were two important things, and now I'm kind of ready to begin discussing RG flows on line operators and line defects. If everybody's fine with that. Let's to get warmed up. Let's do first partition functions. Because I want to discuss this constant that was brought up by people here. It will be important for partition functions. So by partition functions, I mean that instead of discussing RD minus 1, 1, where the line defect has an obvious Hamiltonian interpretation, you can do Euclidean you can do a weak rotation, go to RD, and then you can consider line defects which are some closed curves, closed smooth curves. And you can ask what is the partition function in the presence of this closed curve, ZC, normalized, of course, by the ordinary vacuum partition function with no defect. Okay, this is for conformal defects still. I'm still not yet discussing renormalization group flows. This is for conformal defects. So I'm going to discuss that and the entanglement entropy. Partition functions and entanglement entropy. Okay? So this is the next topic. So first of all, for defects which are trivial in my terminology, like vanishing displacement operator, or equivalently vanishing AI, or probably equivalently vanishing H, this is going to be independent of the shape for small deformations of the shape. So it's going to be almost independent of the shape. And does that mean that it's completely, when I say independent of the shape though, I have to be a little bit careful because of this constant. The dependence on the shape is going to be almost trivial. So let's first discuss the trivial case because I want to explain the significance of this constant. So let's first discuss the case of trivial defects. So for trivial defects, where the displacement operator vanishes, you should intuitively expect that there is almost no shape dependence. But the more precise statement is that you can get some constant, which is called the cosmological constant, on the defect times an integral over the world length. This is going to be a ZC over Z vacuum. What is this cosmological constant? So this is just an integral over the world line, and this is some arbitrary UV parameter. So this whole thing is a counter here. What is the meaning of this thing in QFT? This is the mass. You can think about the impurity as some probe-heavy particle, and this is the mass, which is like up to you to fix. You can just choose it at will. You can tune it to 0 if you want. So even a trivial defect would have some slight, almost trivial dependence on its shape. It's going to be a pure counter term. This is a counter term. Why is it connected to this question? It's connected to this question because it's exactly this constant. Does everybody see that this is exactly the same constant?
What depends on the dilatation?
Right, so under dilatations, for instance, if you took a circular loop, this would lead to an exponential of minus lambda cc times the radius of the loop. So it seems to violate dilatations, even though the defect is conformal. Why? It's because this constant is a scheme-dependent UV regularization. So this constant has dimensions of mass. So you just chose a scheme where there's something that violates explicitly conformal invariance. But it's completely scheme-dependent. It's like in every conformal field theory, when you compute partition functions, there are non-conformally invariant counterterms, which you can choose to tune to 0. Okay?
Can you think about it as a Wilson line?
It's not. It's any line operator. It could be in a magnet. It doesn't have to be in gauge theory.
Suppose that it's n equal to 4 square meters. Could it be a circle of Wilson
Yes.
line?
Yeah.
And it's known that it is independent of the radius.
No, it's a scheme. It's a scheme choice. There is a scheme in which this dependence drops out, but it's a choice of scheme. It's a counter term. You can add it. It's the mass of the probe particle. If you think about it like on the Coulomb branch of n equals 4, it could be the mass of the W boson. So
There I have a spontaneous breaking. It's a symmetry. Here, you just
okay, so
explicitly break.
it's just some UV parameter that's not possible to fix. And this is the same this is the same constant. So even trivial defects have in their partition function some perimeter. Well, this is just the perimeter of the line, basically. They have some kind of dependence like that. All right? Now, what happens for non-trivial defects? So if you're an experimentalists that do measurements on a Euclidean lattice would see this dependence and they could say, oh, we found a conformal defect. But no, you have to demand that the experimentalist proves to you that the dependence that this person found is not just e to the minus lambda cc times r for circular defects or more general defects. It's not just that. Because if this is the dependence of the partition function on the curve C, it means that this person found a trivial defect. Okay? So such a dependence of the partition function is not a telltale sign of a non-trivial defect. It's the opposite. So you could add another statement if you want, that a trivial defect is going to also have this partition function. So this is a partition function of a trivial defect. So it's another diagnostic for what the triviality means. Okay, so now let's do non-trivial defects. When the defect is actually a non-trivial conformal fixed point of the renormalization group flow, the partition function of on a generic shape is going to be unwieldy. We don't know anything about it because, well, we can start from the circle, but then we have to put displacement operator correlation functions to deform the circle to something else, but nobody knows all the displacement operator correlation functions. Actually, there is one person in the audience here that's trying to solve it in the large n limit of some gauge theory. Maybe Deliang is here? Yeah. So this is it's completely unwieldy. Even in simple models, we have no idea what that is. But for circular shapes, you do get something that is beyond a cosmological constant counter term. So what do you get? You get a cosmological constant counter term that you can just remove if you like. But you can get a new contribution, which is a constant, independent of the radius. And this is called the quantum dimension of the defect, in analogy to some terminology in quantum information theory. It's not an integer, and it could even be negative log g, but people sometimes call it quantum dimension nonetheless, because of some connection to quantum information theory that, if you want, I can explain later at some point. So people call it either the g function, or the quantum dimension, or the defect entropy. These are all or the defect entropy.
Is this the same G which appears in boundary series?
Well, I'll get to that. This is in any dimension for now. Okay, so if
G has to be positive.
log g has to be positive, otherwise, yeah, G has to be positive by unitarity. So using unitarity and CPT invariance, it's possible to prove that G is non-negative. Log G, however, could be both positive and negative. It seems that for Wilson lines, it's always bigger than 0, log G, but it's a conjecture. For magnets, many examples exist where log G is arbitrarily negative. So there are many line operators with negative log G, Wilson lines, for some reason, have a positive log G as far as I have seen.
If I take R to 0,
This is a counter term. It's meaningless.
yes, still the G is the same G.
Yeah, the whole point is that if you're an experimentalist and you somehow measure the circular partition function of a circular Euclidean defect, condensed matter people don't know what the hell is this. Because they have Lorentzian time and they have a defect at some point in space. How are you going to make it circular? It's kind of science fiction for condensed matter people. But it's a very interesting observable nonetheless because of some connections that I'll explain soon. So if you're an experimentalist and you somehow measure this in a Euclidean lattice, and you see that on top of the perimeter dependence, there is some constant, then you declare victory. Then the defect cannot be a trivial defect, roughly speaking. Okay?
But again, it's only for circular.
Yeah, for an arbitrary shape, there would be a complicated dependence on all the cross ratios of this shape.
Yeah.
All the dimensionless. Like if you take a rectangle, there could be an unknown dependence on this side versus this side, and how there is no way to determine it in general. But for a circular shape, it's just the quantum dimension shows up.
In analog to old days in gauge theories, you can write some kind of a loop equation.
Yeah, the loop equation is, well, there are some proponents of this here, but the loop equation is essentially void of content. It's just a statement that small displacements correspond to insertions of the displacement operator. What are you going to do with it? You still have to find all the displacement operator correlation functions to compute anything. Okay?
So, can you actually separate the G versus the
No, I don't think so actually. Yeah, you're probably right actually. Nobody has ever seen a defect with G equals 0. That would probably be some kind of disaster. Probably SL2R symmetry does not allow G equals 0. Probably, yes. But people have found arbitrarily small but positive G's. So in some large N models, there are examples now where the quantum dimension is e to the minus n, where n is a huge number. So such examples now exist with an arbitrarily small but positive quantum dimension. Yes.
For this case, why do you think there is no 1 by r corrections and it stops at log G constant?
You're asking why the partition function cannot contain other dependence on R?
Yeah.
So this dependence on R violates conformal symmetry, but only by a counter term. So therefore, this is going to appear if you do a lattice model. It's just going to show up. You cannot tune this counter term on the lattice to 0 so easily. You have to modify the impurity Hamiltonian by a constant. Basically, that's what it means. Change the. If there was an additional R dependence here, it would immediately mean that there is an RG flow because it wouldn't be a counter term, and it would not be consistent with conformal invariance. So therefore, this is the most general allowed dependence of any line operator in any number of dimensions for a conformal line operator. Okay? And yes?
So, what actually happens in the lab, so let's say I take the spin S you presented yesterday.
Yeah.
The more I enlarge the spin, the smaller G is going to become or something like that.
Yeah, you're asking what is the value of log G in the Kondo problem in higher dimensions?
For example,
Yes, so if you put a spin S nucleus, if spin S nucleus is your impurity, you should expect that log G is, roughly speaking, a log of 2s plus 1, because that's the dimension of the Hilbert space of your impurity. But interactions will change that answer. So this is only the answer maybe in the free fixed point. So this line operator with spin S atom would have many fixed points. One of them would be a free fixed point, where there is no interaction with the bulk. Then this would be correct, exactly. Because if there is no interaction in the bulk, this is just the partition function of the quantum mechanics on a circle. Like, imagine that the impurity doesn't talk to the bulk. What is this? This is the trace of the Hilbert space of the impurity. So it's just the number of ground states of that system. And it's going to be 2s plus 1. But as soon as this interacts with the bulk, this result could change. And it could even be negative in some examples, as I said.
must be talking about, because we're not talking about the displacement
Right,
displacement
right.
is
If it
not
doesn't even talk to the bulk, the displacement operator would identically vanish, and it's a question. I would call it a trivial defect, but you could say it's a trivial defect with a ground state degeneracy. There's lots of semantics. When I say trivial, for these lectures, I mean vanishing displacement or vanishing energy momentum tensor. But some people would say it's not trivial because there is ground state degeneracy on the impurity. So it's a question of semantics, whether you want to call it trivial or not. But either way, this would not be the full quantum answer.
Yeah, but generally speaking, G goes with S.
You could, it depends on, yeah, you could say that, but I mean, yeah. If you look at the Kondo problem in 2 + 1 dimensions, yes, it does grow with S, but it's not going to be this answer. Any other questions? Okay, so this is the partition function of a conformal defect. And okay, so now we're ready to finally discuss what is the meaning of that in, let's say, more Lorentzian, in a Lorentzian interpretation. I'm still talking about conformal defects. I haven't begun RG flows. So you could ask, okay, this is an interesting observable. It's the partition function of a circular conformal line. But how do we make contact with the experiment? Like, how is this going to be measured? And so for here, I just want to remind you of that fact, that the one-point function of the energy momentum tensor in the presence of a line defect vanishes in 2 dimensions by conformal invariance. So this is going to be crucial. So now let's go to 2 dimensions. In 2 dimensions, there is a beautiful answer of how to measure it in Lorentzian signature. So you take, this is a space-like slice with the defect. Okay, so this is the space-like slice with the defect. And what you do is you take an interval which surrounds the defect symmetrically from both sides. You compute the density matrix of the vacuum restricted to that region. So you just trace over the complement for the vacuum in the vacuum with the defect. So there is some vacuum. You trace over the complement of that region. Then you compute the von Neumann entropy of the density matrix. Trace rho A log rho A with the minus sign. And then you subtract the entanglement entropy of the ordinary vacuum in region A with no defect. You subtract the entanglement entropy of that same interval, but with a trivial defect. The claim is that this is exactly log G. So log G captures the additional entanglement of the vacuum due to an impurity exactly in the middle. If the impurity is not in the middle, it's not known what does it measure. But when it's exactly in the middle, it captures the additional entanglement of the vacuum. Additional, I mean, because we subtracted the vacuum entanglement. So you don't see the famous Cardi-Calabrese logarithmic dependence on the interval. I've subtracted that out. So you just get log G.
Why do you do the subtraction and not take a relative entropy?
Relative to what? What?
Well, relative entropy will mean that in the other term you take rho A log of rho vacuum.
Yeah, I'll get to it soon. This is just the correct formula as I wrote it. Okay? This is just additional entanglement in the vacuum due to the defect.
It could be negative.
It could be negative, yes. So the defect could decrease the entanglement of the vacuum with the outside. And actually it is negative, for instance, in the defect that we spoke about yesterday with an external magnetic field in the 2D Ising model. So there are many examples where it's negative. Yeah, intuitively I believe the following can be said. So if you think about the vacuum as just a bunch of little oscillators that talk to each other. So now let's say you have an impurity here. So it could be that the impurity pushes the wave function away. So the wave function, the vacuum has some kind of wave function. And it could be that the probability of finding excitations, any excitations in the vacuum near the impurity is smaller than what it would be without the impurity. So it's like the impurity is pushing excitations away. So that's what it would mean.
Why does it have to be so?
Yeah, it's not possible to understand, but it's only when it is symmetric that we have analytic results. I think people would probably consider this also at some point, where it's close to the boundary, because then you can do a OP. But for now, only the symmetric configuration has been worked out. Okay, so this is only true in D equals 2.
It's independent of the size of where you put the
Interval?
Yeah.
Yeah, because of conformal invariance. Where the fixed point in the bulk, fixed point on the defect, so it's independent. When we get to our G-flows, it will of course depend on the size of the interval. But for now, it's independent. So this is the correct result in D equals 2. And you could ask, what about the quantum dimensions for line operators in higher dimensions? So it turns out that this formula is not true. But you get a correction. Let me just write a correction. So now I can remove the label D equals 2. Now I'll write a formula that's correct in every dimension. So you get minus D minus 2 over D times H. And there is some constant here. I don't have enough space to write it here. I'll just write a constant here. The constant is 2 pi times the volume of SD minus 2. Okay.
This is when you, the A is now a ball.
A is what? Sorry.
D greater than 2, A is now a segment for the ball.
Oh, yes, yes. So we surround the defect with a disk, in which the defect is exactly in the middle.
So it is in the middle of the ball.
Middle of the ball, yes. It's in the middle, in the center of the ball, in general dimensions. It's a D minus 1 dimensional ball, which surrounds the defect. And you get this correction from the one-point function of the stress tensor. So log G is not directly visible in the entanglement entropy. There is another thing that creeps in. But actually, Kobe had a very prescient comment. It is indeed true that you can define a more complicated entanglement entropy, like a relative entropy, in which this goes away. But it's a very complicated construction that appeared only last week. People have been searching for it for some time, but last week there was a paper by the usual suspects, Cassini, Landea, Toroba, in which they figured out some version of relative entropy with some light cone boost. It's a very complicated construction. It's a sequence of entanglement entropies which approach the light cone in which this goes away. But anyway, this is the fact. So this is the connection of this partition function to entropy.
No, I have a problem. You said that it's independent of the size of the...
Yeah, it's independent of the size.
When you send it to infinity?
It's independent of the size. What? Why 0?
Because there is no outside now.
Oh, for pure states, there is a theorem in quantum mechanics for any finite system. The entropy of any region is the same as the entropy of the complement of that region, regardless of the size. I don't know, like. So when the complement, it's an infinite space. I'm talking about entanglement entropy in infinite space. So there is always outside. Anyway, now there is a suggestion for how to remove this piece, but it's not something I want to cover.
Do you want to remove the H? In other words, before you were saying H is important.
Yeah, H is fine.
Like
H is fine.
number.
It's just that you're going to see that there are important theorems about this. And these theorems, it would be nice if they had a quantum information theoretic interpretation. So something in terms of some entanglement. So it was a challenge for some time to find a quantum information theoretic observable that picks up only the quantum dimension without this correction. And now there is a suggestion. So there wasn't a suggestion like last year. Now there is one. But in 2 dimensions, it works out more or less automatically. Okay, so this finishes conformal line operators. And I want to now talk about RG flows and what's known about this quantum dimension log G, how it evolves as a function of the RG scale. Yeah.
How do you show this way? If the around the defect gives you the log G.
How to show this? You mean in D equals 2 or in any number of dimensions? In D equals 2. So it would take me a little bit too far afield. I kind of don't want to jump into that. In 2D, the way it is shown is by something that's called the folding trick. Because in 2D there is this, I won't be able to explain it if you are not familiar with it. So I'm just quoting these results to give you some perspective. Okay, so RG flows. So when we have a line operator L, it's not necessarily tuned to a fixed point, obviously. There are in general parameters that can flow. And the picture that we have to have in mind is, sometimes people call it DCFT. It's a conformal defect. DCFT is a defect conformal field theory. So people write DCFT when they mean that the line operator has been tuned, or the defect has been tuned to a fixed point. So in general, there is an RG flow between an ultraviolet defect and an infrared defect, both of which are conformal. So there is an SL2R symmetry in the infrared.
Will also bulk?
Bulk never flows.
Bulk never.
So my bulk is always a CFT in D space-time dimensions. Bulk never flows. The flow is by some parameters that exist on the impurity Hamiltonian. So there is some mass scale mu on the impurity Hamiltonian, and that evolves. All right. So now the main thing that we know. The main one, so there are many examples of that, of course, but I just wanted to quote one general theorem about this situation, that there is an RG flow. So one general result. So it is useful to consider the expectation value of a circular defect again, but now we're doing a Euclidean continuation, of course, but now it's not going to be a simple function of the radius as before, because we have the counter term, which is just ambiguous, but then we have some log G, which could be an arbitrary function of mu r now. Mu is the fundamental scale on the impurity Hamiltonian, and r is the radius of the circle. So there is some unknown function. It's more messy now. And this unknown function would go to a constant, to some constant in the UV, and to some other constant in the infrared, and that would be achieved when r goes to 0, and this would be achieved when r goes to infinity. So you can think about the radius of the circle as some sort of proxy for the RG flow. So whether you go to long distances, it corresponds to large circles. Short distances corresponds to small circles. So this function evolves. So what is the main result? The main result is that if you take the logarithm, you can take the logarithm of this expectation value. That gives you the numerator here. But this numerator contains a piece which is ambiguous. Sorry, it's r, because it's a circle now. This numerator contains an ambiguous piece, which is due to this counter term. So it is useful to act on the logarithm of the expectation value with a funny operator that looks a little dumb, but all it does is to remove the linear piece. Okay? So you could say that this is a scheme-independent function. So this is a scheme-independent version of the partition function of the circular line operator. And what is the main result about this function? The main result about this function is a certain identity that we actually know how this function evolves as a function of the radius of the circle. And it's given, there is a minus sign, and then there is an integral. I'm going to write the answer as an integral over two angles, which correspond to the locations of an operator that appeared before. So all the things we saw before are going to come in now. So this is connected. This is the connected two-point function of the energy density on the defect. And it's multiplied by 1 minus cosine phi 1 minus phi 2. Let me just erase that to make the formula a little bit more clear. So this function S of R, which is the circle partition function roughly speaking, has a very nice identity that if you try to track it from UV to infrared, there is minus, this is the size of the circle, then you have to integrate the two-point function of the energy density theta operator. You remember that this operator theta vanished at the fixed point. Why is it good? It means that this whole thing vanishes at the fixed point. Why is it good? Because f should be a constant at the fixed point. It should be just the quantum dimension of the corresponding conformal line operator. So it's consistent. But if there is an energy flow, as I said, the impurity could absorb and emit energy. So now theta is a non-zero operator. And its two-point function weighted against some cosine gives you a formula for the evolution of this S function. And this is just manifestly negative. Because the two-point function is positive in reflection positive theories, unitary reflection positive theories, and this is a non-negative weight. So this is positive, this is non-negative, this is non-negative, and there is a minus sign. So the whole thing is negative, is non-positive.
The phi's are coordinates on the circle.
Yes, and the phi's are angles here. So I just parameterize locations by the angle phi. Phi is just the angle on the circle. Okay, so this is a nice formula that proves an important theorem that we will use in applications soon. It means that S is a monotonically decreasing function, monotonically non-increasing function, and that in particular means that the quantum dimension of the ultraviolet is always not smaller than the quantum dimension in the infrared. This is a corollary for the defect quantum dimension.
This, high enough dimension, this could be singular.
Okay. So David is asking, why is it obviously convergent? So, right? So the point is that theta is the energy that's stored at the defect. So in any number of dimensions, this is a dimension 1 operator, because it has dimensions of energy. So therefore, the worst possible singularity when the 2 points approach is 1 over phi squared. And this is miraculously cancelled by this 1 minus cosine. So therefore, this is a finite integral in any number of dimensions.
Yeah. This theta would be dimension 1.
Yes. Yes, the theta is dimension 1 independently of the number of dimensions.
How is this result obtained?
How was this result obtained? Well, the first step is kind of obvious. The first step is that you try to understand what happens when you change the radius of the circle, of the defect of the circle, right? That corresponds to a RG transformation, which corresponds to an insertion of theta. So you can see that these derivatives are closely connected to the theta insertions. So this is not hard. It's not hard to see why there would be some theta insertions. This is very difficult to understand. It's very, very difficult to understand of where this comes from. Yeah.
Do you have interpretation of that also in the language of this entanglement entropy?
Right. So, as I told you, in 2 dimensions, the entanglement entropy due to the impurity is on the nose coincident with log G. So it is also true, therefore, that the entanglement entropy due to the impurity decreases monotonically, roughly speaking, in 2 dimensions. But in higher dimensions, it's much more complicated because log G does not appear in the entanglement entropy of the ball with an impurity inside. Well, it appears along with other things, so you have to do something much more sophisticated. Okay? Okay. Yeah.
Is this in 2 dimensions or in general?
This is for any D.
So the phi spherical value on the sphere, like not on the circle, right? Like it's not angles, it's
No, I'm talking about line defects in any number of dimensions. So this is some circle on a plane in any number of dimensions. Any other questions?
If there is no bulk, this is the pure quantum mechanics.
Okay, so Shmuel is asking what happens if there is no bulk, and you're asking if there is no bulk, would that be a theorem in quantum mechanics? So if there is no bulk, then basically this partition function is gonna just compute the number of degrees of freedom in the quantum mechanical on the impurity, and it's not going to lead to any interesting result because theta here. The answer is that it doesn't lead to anything interesting in quantum mechanics. It's only interesting and contentful when there is a conformal bulk. And also the derivation of this formula uses the fact that there are non-trivial correlation functions of the energy momentum tensor in the bulk. So if you try, we've tried at some point to see if it has any implications for quantum mechanics isolated from the bulk, and the answer is no.
So this is the analog of the C theorem.
Yeah, it's for odd dimensions though. It's a theorem for the G function of line operators. And what I'm going to show you next is we'll go over lots of examples of line operators in QFT, and I'll show you examples of our G flows and fixed points because I've given you some theory now, but time has come for some applications, so let me just list the applications that we'll go over. Some will be more from condensed matter, some will be more from high energy physics. So I'm just going to make a list of examples that you can start thinking about in your spare time. So the first example that we'll go over is the path ordered exponential of the integral over scalar field. This is a very cute line defect. And the bulk field theory will be just free field theory in 3+1 dimensions. Okay, this is going to be the first example about free conformal field theory in the bulk, scalar line defect integrated at x equals to 0. It corresponds to an external magnetic field. This is the first example. It's a very clear pedagogical example where many things that we have seen come to play. Then, of course, we have the path order.
Why is it a conformal defect?
Well, you can see it kind of just from dimensional analysis almost. In this example, there is not going to be an energy flow. It's going to be conformal out of the box. So it's going to be SL2R invariant right away. SL2R times SO3 invariant without any further tuning. Because phi has dimension 1 in mean field theory in 4 dimensions. So this is a dimensionless integral. So gamma is dimensionless, and it turns out that it has no beta function. So this is going to be a conformal line operator in free field theory in 4 dimensions. Yes?
Sorry, why do you use the path operator?
It's just because when you use, you can think about, if you think about it as an insertion in the path integral, sorry, what? I lost. Yeah. If you think about it as an insertion in the path integral, you just change the action by adding d3x, dt, d3, delta 3x, phi times gamma. This is an insertion in the action. Once you think about it as an operator insertion, if you want to think about it as an operator, you have to always, you remember that correlation functions in the path integral formulation come out time ordered. So my pass ordering is the same as time ordering. So if you think about it as an operator, it has to be time ordered. Yeah.
I actually got to be sure, but is the action bounded from below the action with the insertion?
Yeah, the action with this insertion is not bounded from below,
So right,
but it doesn't matter. It's a counter term. You can renormalize it away. You can think about it as something that happens locally at defect that you can remove.
yeah, but just take phi everywhere in space, you look at it for space and time, and just slide it to the space more and more. If gamma is positive, make it more and more negative.
Yes.
And the action will be smaller. So I don't see why the function rating will converge.
So there is, you could, let me just respond to it in a maybe slightly different way. So you could try to do this in d dimensions. It turns out that d minus 1. So let's say 2 plus 1. In 2 plus 1, the instability that you mentioned is actually disastrous. This doesn't make sense. It doesn't flow to an SL2R invariant fixed point. But there is an energetic argument that I'll explain where in 3 dimensions, it's actually, in 3 plus 1, it's actually fine. It doesn't lead to a disaster. It does flow to an SL2R invariant line operator. But in lower dimensions, there will be like some dynamical instability creating this.
Space is compact or non-compact?
Here it's infinite.
Then why couldn't the whole thing just slide?
It doesn't in 3 plus 1. It just doesn't do it in 3 plus 1. It's an argument about energetics, so some cost of energy of some bubbles. But in 2 plus 1, it leads to a disaster. That's why I'm not talking about it. In 2 plus 1, it does lead to a horrible disaster. It's a relevant operator in 2 plus 1, but it doesn't flow to a fixed point. It just destroys the vacuum. But in 3 plus 1, it's fine. In fact, this is a piece of the supersymmetric Wilson line that David and Juan worked on. So it could have exactly the same issue. He could have asked the exact same question. There is the supersymmetric Wilson line has such a piece with no I, so it's exactly the same thing. And
You could take phi squared, which is based on
okay, if you put here phi squared, it would be irrelevant, and gamma would flow to 0. It would be a trivial line defect in the infrared. In 3 dimensions, this is a very interesting problem. So you could do 2 plus 1 and put phi squared. This is a very interesting problem. It's still free field theory, but now it's marginally irrelevant. And it turns out gamma flows to 0. So the fixed point turns out to be trivial. So I'm going one by one. This is the simplest example. You can just solve it. The second example is, of course, a Wilson line in Maxwell. A Wilson line in Maxwell theory. It's IQ integral over 8, 0 dt. This is another conformally invariant line operator in Maxwell theory. A free Maxwell theory. So the theory is going to be f squared d3x dt. 1 over 4 e squared. These are the 2 pedagogical examples where you can warm up and compute the g function. Here q is an integer. Q is an integer, while in the previous example gamma is any real number. And the third example will already be interacting. So the third example we'll talk about will be some example that's motivated by condensed matter, which would be the pinning defect and the Kondo defect. I'll say a few things about those. These are non-abelian versions of this guy. So it's like a non-abelian version of the first example. And then the final topic would be Wilson lines and Hooft lines in non-abelian gauge theories, where there is a complicated RG flow and many new fixed points. It's a long story. So the last example will be Wilson and Hooft lines in non-abelian gauge theories. Just to give you some motivation, you know that people have for a long time said that S-duality exchanges Wilson and Hooft lines, but you'll see that it's a much more complicated story because Wilson lines have multiple fixed points, and many of them don't even have fixed points. So the map is actually very interesting. It's not obvious how it works in, let's say, n equals 4 super Yang-Mills. So I'll show you later if I get to it. Okay, so I want to start from the first example. In the last I have like 10 minutes, right? Yeah, so I want to start from doing the first example in the last 10 minutes. So the theory that we want to study, we will go to Euclidean signature. We're going to go to Euclidean signature. The theory that we want to study is d phi squared with a half plus delta 3x d3x dt phi, and the parameter here is going to be gamma. So how do we attack this problem? It's a quadratic field theory. What is the first thing? How would we? How do we solve such a model? Anybody has a suggestion? Yeah. You have to decide what do you want to do. One problem you could solve is just take a straight line. I haven't specified. So this is this setup. Take a straight line and measure some one-point function far away from the defect. This is one problem. Take a composite operator like phi or phi squared. You can take phi or phi squared and measure a one-point function away from the defect. Another problem you could try to solve is to take a circular defect and compute the partition function. That would then you would need to write a slightly different action, where the integral is over a line, over a circle. Okay. So let's begin with this problem. It's much easier. So how do you do that in principle? So you could either just think about it as a perturbation, lower it from the action, and compute weak constructions, or you could solve the equations of motion. Any of those things would be as good as any other. And so your homework, I'm going to give you 2 homework exercises for today. I'll solve both of them tomorrow in my next session. So homework problem number 1 is to compute phi, which is going to be some function of the distance from the defect and gamma. Argue that gamma is exactly marginal. You can try to compute phi squared as well if you're super motivated. How do you argue that gamma is exactly marginal? You would see that the AI, the coefficient, the one-point function, some function of gamma, there are no logarithms, no violation of conformal invariance. So argue that gamma is exactly marginal. The second thing is to try to compute log g, the quantum dimension of this defect. Now here there is a shortcut. You can anticipate the answer without any work. So let me show you how to anticipate the answer, and then maybe you can try to prove it, and you'll see that it kind of works magically. So remember that we had an identity for how the quantum dimension changes as a function of the radius of the circle, which roughly speaking was some 2-point function of theta times 1 minus cosine. So a very interesting and kind of obvious corollary of this word identity is that if you have an exactly marginal perturbation, since theta vanishes at SL2R invariant line defects, this has to be 0. So that means that if we started from some quantum dimension, log g, you added this perturbation, namely you changed gamma a little bit, there is not going to be any change in the defect entropy. Because throughout this whole process, the energy density on the defect vanishes. The energy density defect operator vanishes. So therefore, this implies that exactly marginal operators cannot change g. So therefore, log g has to be gamma independent. And it has to come out miraculously from the computation. Since it's gamma independent, it's extremely easy to evaluate. You can evaluate it at gamma equals 0. At gamma equals 0, there is no line defect. It's the unit operator. And therefore, the ratio of this partition function by the vacuum partition function is 1. So therefore, this is 0. Okay? So you can, it comes out kind of miraculously from, to compute this partition function, you have to sum over infinitely many modes by solving the equations of motion, finding the eigenmodes, and you'll see that gamma drops out at the end of the computation. It does not drop out from other shapes. If you try to consider an ellipse or a rectangle, gamma would not drop out. It's a genuine exactly marginal operator. But it drops out from the circle because of the connection to this entanglement entropy and the RG flow monotonicity. Okay, so these are two homework exercises about this model.
Is there any interpretation what this coefficient means when you check, because now you have a moduli?
Yeah, it's an exactly marginal operator.
But what is it? Does gamma?
It's the external magnetic. It's the external magnetic field. So the way you realize it on the lattice is that you have spins, and you just put, let's say you choose 4 sides randomly, and you put an external magnetic field with coefficient lambda. Since the bulk is going to be in mean field theory, you know that like mean field theory is the answer for the magnet and the ferromagnet transition. Mean field. So the bulk is going to be free field theory. This line operator that describes an external magnetic field that's localized on a few lattice sites is going to translate to that in the continuum limit. And the fact that gamma is exactly marginal means that it's not, you know, that the value of this external magnetic field does not flow as you do spin block transformations. So it has a very clear meaning, and these are some 2 exercises just to warm up. So I'll do them both tomorrow, and we'll go to the next ones. Okay, 5 minutes if there are any questions. Yeah.
Can you also consider higher dimensional defects?
Yes, I'm not going to do it in this course, but higher dimensional defects describe, you know, not just localized impurities, but some extended impurities.
And then do you get something in the same form, like if the expectation value of 3 vanishes, b equals 3 or something?
I haven't looked at that, to be honest. I don't know. I haven't looked at this question, but it's very easy. It's the same technique. You can determine the answer by symmetries, conservation, and tracelessness. I don't know off the top of my head if a codimension 2 defect, you know, leads to a vanishing p in every dimension. But it's a very easy exercise. Yeah.
Is there any sort of G theorem for codimension, higher dimension?
Yeah. So the question is just maybe the question is whether there is some analogous statement for higher codimension defects, lower codimension defects. So for instance, for a surface. So a surface defect describes an impurity extended along a line. And you can ask, is there some monotonicity theorem for the partition function of a spherical surface defect? And the answer is yes. It's not as, the answer is basically yes for a spherical for surface defects. But if you look at 3-dimensional defects, maybe no. Maybe there isn't yet an established answer. Yeah, but for surface defects, there is something pretty close to what I'm saying here. There is a story that's very much close to it, yeah. Any other final questions?
If the defect is trivial, is it the same as one from symmetry?
Okay, so this is the good question. Maybe I have 2 minutes, I'll explain that. So I'm using a notion of triviality.
Can you repeat the question?
Yeah, the question is what is the connection of these defects in higher symmetries, basically. So I'm using here, I used a definition in this course, which is, for me, trivial / screen is the same as vanishing displacement operator, which is conjecturally the same as many other conditions I mentioned along the talk. This definition is not completely satisfactory if you want to take into account topological things. So, of course, a QFT in D dimensions, or CFT, doesn't matter, in this space-time dimensions, could have line operators with vanishing displacement operator, but you would not say that they're trivial. They could depend topologically on their shape, and they could also depend topologically. Let's say there could be another line that if it wraps that guy, then there could be some phase due to the knotting. So you wouldn't say it's completely trivial. You could say it's topological. Now, for a QFT in these space-time dimensions, to have a line operator which is topological, but not trivial, requires what is now called a D-2 form symmetry. So it's a higher symmetry. So nowadays people would say that if a topological line exists, the theory therefore has D-2 form symmetry. This makes sense, for instance, in 2 dimensions, a topological line is a nether charge, right? So it's a 0 form symmetry. It's an ordinary symmetry. In higher dimensions, it would be a D-2 form symmetry. The reason that I'm not emphasizing this very much is because in all the examples that we would look at in this course, except maybe at the very end when I discuss S-duality, there won't be any interesting higher form symmetries. So there won't be topological lines. But in principle, yes, you have to make a more careful distinction between screened in the sense of invariant under small deformations and truly trivial, meaning that it's the unit operator. Any other questions? Okay, thanks very much.
Let's end the speaker.